Okay, very good. So I think from the first part, we learned a lot about the experimental data, what they constrain. Just one thing I wanted to mention before leaving you, something that we will go back to it tomorrow, but somehow wrap up everything we said in the morning, is that, so that's what really means to take the leading order cross-section. So you have parton A, B going into something that has mass m squared. So you always have a delta of XA, XBS. That's what I wrote before. So very often one looks at the kinematics. So I say, okay, that's a number plus this delta function that just tells me what are the X1 and X2 that are needed at leading order to produce a particle. So a quantity that people often look at is this parton luminosity. So it really tells, given something, an object of mass m squared that I'm producing, what is the parton luminosity? So what is the luminosity for parton A and parton B giving me that object at that mass, okay? So these are the quantities that we often look at. I tell you with an example what I mean by that, because very often you do actually see this kind of plots. So for example, let's say I want to know what are the parton channel that create a W boson at the LHC, okay? So, and you see here that if you run, for example, MadGraph or any other generator, you can check what is the parton content of each of the event. And you can see that at 13 TV, you get 80% of the events come from an up and a D bar quark, and then you have 20% that come from a D U bar and so on. And then much less from all the other parton channels, okay? Or again, you run a Monte Carlo generator to see the Z boson production, and you see that at the LHC, most of it comes from UU bar and DD bar. So then what do you do? So this is the main channel. So the thing you might want to look at is the parton luminosity for the UU bar. So what does it tell us? So this is the UU bar parton channel, okay? So what is the PDF? So the contribution from the proton structure function from the UU bar channel as a function of the mass. So you can see that this is a function that grows as you go to lower values of the mass. And what is the uncertainty we have on this channel? So then you zoom of it. So you just normalize it to some central distribution, and you see that if you normalize it, for example, to NMPDF 4.0, you see that this is the luminosity that we know with, for example, if you say, if you produce something that is 100 GeV heavy, you have this error bar on it. So you have 10% uncertainty on the parton channel. So basically the trick is look at leading order, what is the parton composition of any process you want to calculate, plot the parton luminosities. So this tells you how, for example, in this case, it tells you that the content, so the heavier is the object, the smaller is the luminosity from the partons that you get. And then once you normalize it to a given one of these three possible fits that you can look at, this tells you for a given object what is the uncertainty on the proton structure that comes from that particular channel. Is that clear? So we will look at it more tomorrow, but just to say, everything I told you can be summarized into this thing. So how do you know what the partons have to do with the particular cross-section? Okay, so you look at this, then we can talk about it more. But anyway, that's just to wrap it up. So now the question is, this uncertainty, how do we calculate them? Okay, so now we know everything about the data that go into a fit. Given a bunch of data, how do we know what is the residual uncertainty? So this is quite of a complicated game because you're not fitting one number, okay? So whenever you have a single quantity that you want to fit from the data, the thing you want to give is the 1 sigma error, okay? Or the 68% confidence level for that parameter to be in that given range, or the 2 sigma, whatever you want. If you have multiple quantities, you have the 1 sigma contours in the n-dimensional space of the n observables that you are fitting. But in this case, you have functions. So in principle, you have to give the 1 sigma error band in a functional space, which basically is an infinite dimensional space. You don't have a finite number of points. For all values of x, you want to give an error, okay? So what you really want to do is you want to find the probability density in the space of function f of x. And once you have the probability density, then you can calculate the expectation values for the function or the uncertainty, like functional integrals that are weighted by the probability density distribution that you calculate, okay? So this is what I mean, is that you have an observables that depends on the PDF, and what you do, you integrate over the functional space of the PDFs over the observables weighted by the probability that you have determined, okay? But clearly this is not an easy problem because you have only a finite number of experimental data points and you want to find an infinite dimensional object like a function, okay? So somehow this is an ill-posed problem. You have to go from infinite to finite if you want to find something that uses a finite number of data points. So how do you do? So let's start with the kind of toy model just to understand what we need to do. So imagine that we have a set of uncorrelated measurements, which are these red points, of a quantity f of x at different values of x. And, the underlying law that nature established for this quantity is a sine function, but we don't know it because we don't possess the law of nature, we don't know it. So we try to guess it with the fit, okay? So we want to fit a sine function given this measurement. So what do? You have to choose a parameterization for this function f of x, usually, that's what you do. And you perform a fit by minimizing a figure of merit. For example, the chi-square. So the distance of your prediction between the data. So the chi-square is usually the log likelihood of the data. So you minimize the sum over the number of data of the experimental measurement minus the theoretical prediction divided by the uncertainty on the data points, okay? So here we start with our functional form. We are not quite there because the chi-square per number of degrees of freedom is still much larger than 1. So we are underlearning the law of nature, okay? Here we are there, we are doing a proper learning, as you can see from our parameterization that we input. In this case, I did myself the exercise, you can put just some polynomials, okay? And now we can see that here we have a proper learning. But if we keep learning, I add more and more parameters to my polynomial, I can go on top of the noise of the data, okay? So in this case, the chi-square per degrees of freedom is going to 0 because basically with a flexible enough parameterization, I can fit all the noisy stuff of the data. So in this case, we went too far. So this is a kind of overlearning, okay? So we start fitting the statistical noise. So what do we have to do? So the point is we want to determine the error of our fit, which corresponds to the lack of information that the data provide, okay? So this is the propagation of the experimental uncertainty. Clearly, in the limit of an infinite number of data points and all compatible with each other, these error bands that we associate has to go to 0, okay? But the reality is not that. So for a finite number of data points, we want to have a realistic error band. We want to stop the fit when we have a proper kind of fitting, not when we really fit the statistical noise of the data. So, but actually the actual game is much more complicated than that, okay? So this is the kind of toy model fit that I give. But the actual game is we have 3 plus 3 plus 1 plus 1 if you include the intrinsic charm functions. And we have errors on quantities that are not directly measured, as I said before, because we have a PDF convoluted with structure function. And they all enter in measured observables according to different combinations. But the principle is still the same. So what I told you in this toy model is the same as in the PDF fit. So you want to choose a flexible and clever parameterization for the functions. So in this case, we have to choose 7 different parameterization or 8, depending on thing. You need to stop the fit before you do overlearning and you start fitting statistical noise, and you need a reliable error estimate. So these are the 3 things that we need whenever we try to do a fit, okay? So how do we do that? So let's talk about parameterization first, okay? So usually one parameterizes independently the gluon, the light quark and anti-quarks, the strange, anti-strange, plus sometimes the intrinsic charm. While the heavy quarks are generated perturbatively from the quarks and the gluon, as I said before on the board, okay? So The ideal parameterization doesn't have to be too rigid, because if you put too few parameters, then you might not have flexibility to describe the data, or you might have inadequately small uncertainties in region that the data do not constrain. So in principle, when we do not have any data, any information, the uncertainty should blow up, okay? That's what you want to happen. If it's too flexible, then it's, first of all, difficult to minimize, and then it might develop some artifacts that are driven by the statistical fluctuation of the data, okay? So you want to find the balance between something that is too rigid and something that is too flexible, okay? So how do you do? First of all, this function f, they are not completely free, okay? So we cannot fit any function in the world because we have some constraint. So we have, from the baryon number conservation, we have the valence sum rules, okay? So we know that when we integrate over dx, u minus u bar, we want to get 2. And when we integrate d minus d bar, we must have 1, and the strangeness baryon number is 0, okay? And then from the momentum conservation of the proton, we know that the sum over the momentum, the fraction of momentum carried by all the quark, anti-quark, and the gluon has to be equal to 1, okay? So these are kind of 4 theoretical constraints that we have on the PDFs. So we can have any function in principle that obeys this kind of theoretical constraints. Then, so that's something, let me give you an example of, for example, MSTW 2008. So this is one of the collaboration that produces this fit by using some fixed polynomial parameterization. And then I tell you why it improved a bit. So the simple functional form, at the beginning, to be honest, people were just doing normalization x to the a1, 1 minus x to the a2, because you want the PDF to be 0 when x is equal to 1. And then there were some Regge theory that kind of drives our knowledge of the small x behavior. But then they soon realized that to have flexibility, you need to add some polynomial parameterization, okay? So here it's really an example of the 23 parameters that are in here, because some of those are not independent, because we have these 4 constraints, okay? So you have, you see, no, they all have the same kind of shape. With here, you have some polynomial, square root of x, and blah, blah, blah. And here, I show you later, you can see that the gluon, in this particular parameterization, they had to add this term at some point. So with a different exponent, because otherwise there wasn't enough flexibility. But anyway, this is the kind of thing that people do in a fixed parameterization form. The possible issue here, and this is something that was shown by John Pampling in a CTEC fit, is that what is the issue associated with the given functional form? You are restricting yourself into a specific parametric form. How do you know that you're not biasing the fit by choosing that functional form? Why you could have other functional forms that work as well as the one that you have here. And in fact, I think John Pampling was showing that with the CT10, you know, this was the best fit normalized to its central value for the down quark distribution, this for the up quark distribution. And he was showing that if you just choose a different polynomial parameterization, you can have the same good fit, but it goes outside the nominal error band that you have for your PDFs, okay? So this is something that showed that more studies had to be done for how much can you stretch this parameterization to make it as general as possible, okay? The other thing is, it was this one. So then I'll tell you how the NMPDF was doing the parameterization. But for example, between, you see here, no, CT66 in 2008 and MRST, they had a parameterization that was forcing the uncertainty to remain small in region where we didn't have data, okay? And then these, as soon as there were data in this region, this parameterization was not flexible enough for accommodate this data. So what happened in 2010 is that both the CT collaboration and the MSTW, they added an extra term to the gluon. So this extra plus A, G prime, X delta G prime, and so on. And this, you can see suddenly what happened. The gluon went from being like that to explode at small x where we didn't have data, no? And the same for the CT parameterization. So somehow, this is something that keeps repeating. So more studies have been have been done. So now we have much more, for example, we have Chebyshev polynomial, and we have other kind of polynomial bases that are more flexible, that can accommodate better than a fixed functional form. But for example, in the very latest update of the MSHT, so it was the same collaboration as this, but people changed, so the letters change, but it still starts by M, okay? So you can see here what happened, no, because, so this was the U valence minus D valence at 100 GV. So this was normalized to the fit for this distribution that they had before, okay? So this was the uncertainty on the function. But then they wanted to include some LHC data, and these LHC data were super precise, and they were constraining really well some intermediate region in X. And so they had to completely change the parameterization for this combination. And this gave this new fit, which is the green one, okay, which is completely different from the one you had before. But I think in doing that, they learned that there is another way of doing, you know, this intermediate kind of parameterization that I think, so the hope is that eventually this gets flexible enough that these kind of things do not happen anymore, that you don't have this shift into the value of these distribution, which are simply due to you updating the parameterization because of the problem of flexibility, okay? So I think this is a big progress that has been made in the past few years. And so these fixed parameterization now have been updated to with different kind of numerical tools to be more and more flexible. One way of doing is to use neural networks. So this was an old, before it became so fancy as it is now. In 2006, when I did my PhD, that was the idea that we had to, instead of doing a fixed functional form, we can use neural network. They're nothing magic, so we simply use them as functional form that has more flexibility, and it doesn't include a bias, if you want, in the choice of parameterization that you use. So the idea was that we still had this pre-processing exponent, otherwise the neural network, it's a mess to train, but they can be changed and verify that the fit you find is stable. And the idea is that each of the independent PDF was associated with the neural network here that I call Xi. So you have many more parameters. Instead of 30 parameters, like in the polynomial fits, you have about 300 parameters. So you had the initial formulation, now it changed, as I'm gonna show you, was that we had two input, like X and log X. Don't ask me why, in the sense, you could just have X, but because we have lots of functions that depend on log X, it speeds up the training, adding also log X as an input. So two non-independent input. Then you have this thing, and the output is the PDF at the initial scale, okay, times the pre-processing. And you can write it. So once I wrote it, because once I gave a seminar about the neural network parameterization, and I was told that unless there was an analytical form, they wouldn't believe it. And I wrote it, okay, for the case of a very small network, you can actually write the analytical form. If you have a 1-to-1 network, you can actually write the parameterization in terms of the threshold and the weight that you have in each of the connection of the neurons, okay? It's just a very complicated non-linear function that we know that in the limit of an infinite number of neurons in the intermediate layer can approximate any function, okay? That's a property of a neural network that is exploited for doing regression based on neural network, which is what we are doing here. And again, you know, we minimize the cost function, but that's what everybody does. So everybody minimizes, you know, this is a version of the chi-square like the one I showed you before. Well, instead of just 1/sigma square, you have the covariance matrix because you have correlation between data points. So you don't have just the statistical uncertainty, you also have systematic correlated uncertainty. And that's it. And you do that and you find the fit for the neural network. So the only problem here, which is not a small issue because it gave us a lot of headache, is that when you have such a large parameter space, you need some algorithm that is able to explore it without getting trapped in local minimum. So that's something which is highly non-trivial. And also, when you have a redundant parameterization, you risk of overfitting. Okay, so for example, again, this is a fit for the sinusoidal form that you had before. Okay, this is just the order of the polynomial that you can put. You can see that as soon as you put a polynomial of degree 9, you really can overfit a function and get something that doesn't make any sense, okay? It's not generalizable. So what we use in this way is the cross-validation. So if one looks at the chi-square during the minimization, you split the data into different sets, the training and the validation, and you monitor the chi-square of the training. So this is the one that, so this is the training chi-square, and it keeps going down. In principle, it can go to 0, but this is the validation. So there is a point where the training goes down, but the validation chi-square starts going up. And this is where you have to stop the fit, because otherwise then you go into the overlearning region, okay? So this is a simplification, but that's what in practice we do. And there was something interesting. That's an old result of 2009, but I really liked it. And I still believe it was true, in a sense that there was this, so in the neutrino data, there was the famous NUTEV anomaly. So that basically NUTEV, in fitting the neutrino data, was finding a sine square of theta W that was incompatible with electroweak fit. So there were lots of papers about the NUTEV anomaly, what models beyond the standard model could cause that. Because there was this discrepancy that was more than 3 sigma between the electroweak fits and the measurements. But at the time, I think the strangeness was parameterized, because you remember that the neutrino are very sensitive to the strangeness. And it was parameterized by setting S equal to S bar. So the strange equal to the anti-strange for a simplified parameterization. If instead you include if you want a neural unbiased, any kind of more flexible parameterization for the strange valence and the total strangeness, then the discrepancy went away, because as soon as you include the PDF uncertainty that you get because you're not using a kind of too unflexible parameterization, the NUTEV and the global electrofit suddenly became compatible, because the error band of the fit that you do blows up because of a more flexible parameterization of the strangeness. So this was a result that I found during my PhD, and I was very happy about it. So I wanted to share it. But I think it's important all the time. So we have to make sure that the small error bands that we have do not come from a biased parameterization, but they come from really the data constraints that we have on this. So the situation clearly has changed a lot, because now we have much more constraints. So now we can maybe claim an inconsistency, but at the time it was just artificial. Okay, so now what we did in the last 2 years is that we changed a bit. So instead of using like machine learning just as a kind of interpolating tool, just to use an unbiased parameterization, we use it a bit more aggressively. So first of all, using a single neural network for all the independent PDFs. And you can see here you have gluon, upper, and you also have the intrinsic charm that we discussed about it during the break as an independent parameterization that is there, is not generated from the gluon. Anyway, they all go into this very, very deep neural network. And then the other thing that we did was to use the hyper-optimization that they use in deep learning. So before we were tweaking by hand the minimization in order not to fall into this local minima and so on and so on. And instead now, the idea here is that you do a scan over all the hyperparameters, so including the architecture and all the parameters you have in your algorithm. So the optimizer, the initializer, the stopping patience, the number of layers, the learning rate, and so on. This is all monitored on the test, on the validation chi-square, on the data that are not fitted. So in this way, you basically get a kind of algorithm that tells you not only what is the, so that doesn't just tell you what are the PDFs, but also that learns the better methodology to do it, okay? Again, there are a lot of debates because some people think this was pushed too far and you get too precise PDFs that are just induced by these tricks of deep learning. Some people like me instead believe that these are genuine in a sense. And I will tell you later, you have to do a lot of tests whenever you have this kind of functions in order to check that what you get is stable, robust, and generalizable, because now we're really getting into like problems that have to do with data science as well. You have 5,000 data points, and you have to make sure that you are not biasing your fit with the over-aggressive machine learning algorithm. Very good. Okay, so far we talked about parameterization, but then how do we propagate the uncertainty? Okay, I haven't told you anything about the error propagation. That's the next point I'm gonna touch here. So there are two ways that people can find a probability density. So as I said, you want to find an infinite dimensional object like the probability density from a finite number of data points. So, and you can do that. So there are two options. So if you choose a fixed parameterization, you can project this problem into a finite n-dimensional space of parameters, okay? So your probability density goes from the functional space to the parameter space, where n par is the number of parameters that you choose in order to parameterize the PDFs. And then what you do, you use the linear approximation around the minimum of the chi-square. This is what is called the Hessian method. I'm going to tell you in the next slides. Or the other option for kind of going to from an infinite dimensional to a finite dimensional is to choose a parameterization, but you don't project on the parameter space. Instead, you perform a Monte Carlo sampling of the probability, okay? And in this way, the same observable, so for example, the expectation value of an observable becomes an average over the replicas that represent the probability. I will tell you more about these two methods because these are the two main methods that are used in the PDF fitting communities, okay? Very good. So the Hessian method is used by most PDF fitters. You pick a functional form and you project into the n parameter dimensional space. So then the point is that you have a big paraboloid in the parameter space. You want to find the minimum of this paraboloid, which defines the best fit of the parameters A naught. And to do that, usually you use mean width or some minimization algorithm into a parameter space. And then you shift your parameters by A minus A naught, and you determine the error on the PDFs and on any observables, depending on the PDFs, by the propagation of the error in the parameter space. So in particular, when you assume the linear propagation, you are assuming that the observables that depends on the parameter can be expanded, like the observable at the minimum plus the Hessian matrix, okay, in that space. So you have to calculate the Hessian matrix, which is exactly, so the second derivative of the chi-square as a function of the parameters. And you are assuming that this is a good quadratic problem. So you are always assuming the Gaussianity, if you want, around the minimum when you do this kind of minimization. So, so basically, you have to, so this is the kind of, you have to shift, so you have the original parameter basis, and then you find your minimum, and then you diagonalize and you rescale by iterative method. So you want to go into something that is not band, but it's something like that. So you rescale in a parameter space where all the dimensions get the same contribution. And then you find the Hessian eigenvector basis set. So basically, so once you have rotated, all the parameters of the eigenvectors are the ones that give you the uncertainty in the Hessian approach, okay? And what is it? Then once you have diagonalized this problem and you are in the eigenvector set, the total uncertainty is the sum in quadrature of the uncertainty due to the shift in each of the parameters, okay? So then the problem becomes simple. You take the problem, you rotate it, and then you just sum in quadrature along the n par independent directions. So what is the only problem is that according to textbook statistics in principle, so this is the minimum. Then you want to know how far can you go in the delta parameter space to determine the uncertainty. Usually you do delta chi-square equal to 1 when you have one parameter. You project it down, and this is the 68% confidence level on the parameter AI, okay? That's what you normally do when you have one parameter. And if you, but the problem is that these textbook statistics, delta chi-square equal to 1, work in case of perfectly compatible Gaussian errors. But in practice, this is not the case for PDF fits. So for global fit, you have to introduce a kind of tolerance, so a delta chi-square larger than 1. So you have to increase this contour so that this gives you something that can accommodate the various data. Because what you're saying is that, first of all, uncertainty are not perfectly Gaussian, and there are some incompatibilities. How do I determine this kind of incompatibilities? I find a way to introduce a tolerance. So in practice, you know, this is the reality of the fit. So you try to fit a likelihood function that is like that with a parabola, okay? So somehow you have to understand how to put together all these tensions. So the likelihood, this complicated likelihood, is then approximated, described by a quadratic chi-square with a revised tolerance. So instead of t equal to 1, somehow you check what is the agreement for all the different kind of experiments and what is the level of tolerance that gives you a decent chi-square for all the experiments that you put into your fit, okay? So this is a very rough, a very crude explanation, but somehow one has to say, okay, given that I'm doing approximation and the data shows some incompatibility, how do I have to stretch this incompatibility to get? So in practice, you are blowing up the uncertainty in the parameter space by a factor due to the tension among the data sets. And to do that, you have to check exactly for each of the eigenvector how much the shift that you do by raising the tolerance from 1 to a larger number keeps together all the chi-square of the different experiments you have. And for CTEC6, then I think they also included a more rough, refined concept, but it's similar. You can crudely approximate this by a factor of 10. So if you put a tolerance equal to 10, this somehow gives you a realistic uncertainty for all the parameters, okay? So this is what is done in practice. And also for the MSHT 2008, they do a kind of more dynamic tolerance. So the delta chi-square changes depending on the direction you are taking, because you don't want to take a number that fits all, but you want to take each direction independent. Okay, anyway, just to say that this is something that makes perfect sense, but you have to tweak a bit, and you have the problem of the incompatibility. You have to do some magic trick with the tolerance, okay? Very good. Another idea that is not the Hessian is the Monte Carlo approach. So how do you do? There was first an idea by Gille, Keller, and Kosover in 2001 to say, okay, let's do a Monte Carlo in the parameter space, okay? So instead of fitting the parameter with the Hessian method, you generate lots of replicas of the parameters, lots of top points in the parameter space, and you use this as a Monte Carlo sampling basis. However, it was shown that you needed too many replicas in order to do things like that. So you really needed like billions of replicas just to fit this parameter space. So the idea was revised by some of my collaborators in an MPDF. So the idea was, why instead of doing a Monte Carlo sampling in the parameter space, we don't do a Monte Carlo importance sampling? So you do it in the data space, okay? So what does it mean to do it in the data space? It means that you have your data, which are the, for example, the data, the experimental data, and on top of it, you generate artificial data, which are generated according to the error and the correlation that you get from the actual experimental data. So you generate thousands of data which are distributed around your original data points, okay? And how do you distribute them? You produce them within the uncertainty of the original experimental data, and also if they're correlated, you oscillate them up and down together, or if they're anti-correlated, you anti-isolate one up, one down. So these are univariate Gaussian random numbers such that if 2 points are correlated, the systematic uncertainties, they oscillate in the same direction. And then you have some normalization factor. And if you have 1,000 replicas, this distribution of data fits perfectly the central value. You need 100 replicas to get a good description of the error. You need 1,000 to get a good description of the correlation of the original data sets, okay? So what is the idea? Is that you have all your data, you produce 100 or 1,000 replicas of all your data, and you get a best fit for each of those. The ensemble of the best fit gives you the Monte Carlo something in the PDF space and the representation of the probability density. So that's what it is. So this is the gluon for the NMPDF fit, which is based on neural network for parameterization and Monte Carlo for the error propagation. So you can see that each of the green line is the best fit of a pseudo data that we generate from the original data, okay? And you can see that many of those have very different functional form because you have neural networks, so they're not constrained to be a specific parametric form, okay? But then out of all this mess, so if when you go to 100 or 1,000, you can see that you can find the central value for each of the points. This gives you the central value of the PDF, and you get the 68% confidence level or the 1 sigma error bands for this PDF. So basically, with the replicas, you have generated a Monte Carlo distribution in the PDF space from which you can extract all the correlation, the variances, anything you want from this Monte Carlo sampling, okay? And you can do the same for the observables. So basically, how do you estimate what is the expectation value for a Monte Carlo set? You calculate, for example, this is the W asymmetry, you calculate it on each of the replicas that I give you and you take the average, okay? Or you take the 1 sigma contour in the space. So these are the two alternative methods that people can use in order to propagate the uncertainty. And that's the NMPDF collaboration. Exactly, so this is putting together the two things. I just said that, so I don't need to repeat it. Any questions about the error propagation? Okay, so for those who are on Zoom, there was a question about the systematic uncertainty in the experimental data, which is a very important one. So whenever you, so first of all, the chi-square that we fit, this one. So the independent of the method, you always have to use a chi-square, which is defined like that. And this is the covariance matrix that the experimentalists give us that includes all the statistical uncertainties, the systematic uncertainty, which is uncorrelated, and the correlated statistical uncertainties, okay? So this is a covariate, is a multi-Gaussian, which is correlated, you know, in the direction that we have. The other thing that is very important here is that whenever, so that's somehow how you can write it here, no? So when you generate, so again, whenever we generate the pseudo data, we keep that into account, no? Because you have a normalization factor that we have to be careful with because there is a D'Agostini bias. It's a statistical thing that you can bias the fit unless you treat it carefully. But then here, you always have to use the correlation given by the experimentalist. So what is the problem? Is that in a Hessian fit, you have to do somehow a Gaussian approximation. So you have these asymmetric systematics that you give us have to be symmetrized, I think. Then Alberto can correct me because you do Hessian fits. So they have to be symmetrized in order to then fit the paraboloid with the Hessian approximation, okay? And then you go back and you use the shifting again to anti-symmetrize them. So you have to do a bit of a trick to deal with those. In principle, instead, when you do instead of Monte Carlo fit, you don't need to do any of this trick because we are not using any Gaussian approximation. So each of the pseudo data is distributed in the way that experiments distributed, okay? So in principle, in fact, you do get error bands which are not, which are not perfectly Gaussian. In a sense, there is a difference in the representation of your uncertainties due to the non-Gaussianity that comes from experimental errors. Yeah.
She called me in the...
Yes, go ahead.
No, there are two parts of to this business. One is to figure out the uncertainty on the function that you are fitting, and you can do it at various levels. But Maria, can you go back to the?
Yeah, of course. Sorry.
I don't know which direction to go. To this formula with the systematic error with the generation of the data. Okay, so here the information, the experimental information is given with these sigmas, so the correlated, uncorrelated, all possible things. But most of the time, and I do not have in mind, at least I do not have in mind ever having to deal with an asymmetric experimental uncertainty. But nevertheless, if it is, we assume, because that's the only things that you give out, this is a second moment of your uncertainties, right? We assume that it is Gaussian, because that's the only thing we know. If you give us only the covariance metrics or these columns of systematic uncertainties bean by bean, that's the only thing we can do. And therefore, these are treated using a Gaussian random number generation here with the R's. So the errors, the experimental errors, are assumed to be Gaussian.
Yes.
Because you don't give us any other information. If it is really important that it is asymmetric, it can be treated. In this case, it's very easy, because can you go back to the R? Instead of using the Gaussian, we use the distribution that you should tell me your systematic uncertainty is following. So in a way, it's very simple to deal with, but I don't have any.
But in the parameter space, you have to anyway do a Gaussian approximation when you fit the parameters using the Hessian matrix. No.
But this is the other part. So this is how the data are treated, which was your question, I think. And then there is the whole business of what do we do after. Yes. This kind of thing. So they do this with the Monte Carlo method, which is fine. What we do, we put all this inside inside the definition of the chi-square. But again, if really it is important, instead of doing a log likelihood, we can do another likelihood if really we need to do that. And in fact, there is a very interesting data set that I think nobody has used. It is it is a HERA result in which they looked at a super large X region of the deep inelastic scattering in a very interesting technique. So when they do not see the scattered electron, but for other reasons they know there was a scattering, then they can say this is X larger than. So they have a beam with X larger than at 0.5, 0.4, 0.6, something like that. So very super large X. And that is very low counts. It's a large integrated beam, so it needs a different statistical treatment. If we wanted to put in, it would be great, but it is so much trouble.
How would you do it?
So much work.
You have to add a bit of a Poissonian.
Yeah, you should have some Poissonian distribution, paying attention here. So you should do something. It's possible. It's a lot of work. If it's really important, one can go through. But that is the only example I have in mind of needing a different statistical treatment of the data. Then the statistical treatment of the fit is a different thing, and I don't want to steal the thunder from her. And I have also my own a little bit opinion or experience and things how to do the Hessian fits, how to deform, adapt the Hessian fits to situation of this kind. So there is a lot of activity going on essentially right now on those things. We can discuss this later.
Exactly. Thank you so much. No, you can keep it if you want. I don't need it. I have it here. Okay, cool. Thank you. I think that was, thank you for your question. Yes, and then exactly one thing that is very important for the users is that whenever you are given a PDF from the LHA PDF, you have to know whether this was determined as a Hessian set or as a Monte Carlo set, because then you need to use different formulae in order, for example, if you want to calculate the PDF uncertainty associated to a given set, you have to ask yourself, is that Hessian or is that Monte Carlo? If it's Hessian, then the central value is given by the member 0, of your PDF set. And then the way, again, in which you compute the uncertainty, the PDF uncertainty on a given observable F from a Hessian set is this formula. So you have to take the paired variation along each of the eigenvector. So you take K from 1 to number of members divided by 2, and you pair the odd and the even, and you square up the difference. Okay, that's the way. So you go eigenvector by eigenvector, and you sum up in quadrature the uncertainty on the parameter space. Okay, and this reflects the uncertainty on the PDF. If you have a Monte Carlo set, instead, the central value is given by the average over the prediction for F with the 100 equivalently good fit that you do to the Monte Carlo data. And for example, if you care for the 1 sigma or the variance, you do it with the usual statistical way. No? So it's the average minus so the sum of the average minus the average of this, the sum of the square minus the average of the square, which is the usual formula you have got here. Okay, so one has to be careful because sometimes experimentalists misquote the PDF uncertainty using different kind of uncertainty treatments. Yes. Basically, everything apart from NMPDF is Hessian. So MMHT, which is a new version of MSTW, I think now they decided the final acronym, so it doesn't depend on the members of the collaboration. I think now it's MSHT, and it stands for some minimal something. So they got rid of the names because it kept changing and it was confusing. But basically, all the sets here are Hessian, and the NMPDF is Monte Carlo. And I'll tell you, yes, of course, GEM. GEM is Monte Carlo. I should add it here. Yes, you're right. Yes, you can. Each of them is like self-consistent. And again, in principle, so NMPDF does GEM use, for example, parameterization and Monte Carlo? So you don't have to do neural network and Monte Carlo. So for example, you can do fixed parameterization and fit the fixed parameterization on the Monte Carlo replicas. And this would be another Monte Carlo set based on a different kind of parameterization. NMPDF decides to put together neural network and Monte Carlo, but you don't have to. Yeah,
and GEM does that instead of enlarging the parameter space, they try to put together many more observables, semi-inclusive fragmentation, final state fragmentation, and so they try to do much more global analysis, but so the number of parameters
more Q squared. Yes, exactly. Yes, exactly. So as long as you know, you can actually, that's what I'm going to talk about tomorrow. So you have different prediction if you use different PDF sets. So how do you know which one is right, which one is wrong, where the differences come from? But to do that, we first have to go through all the ingredients. So I think today we try to lay the foundation of understanding the ingredients that go into a fit, and then we can judge, what you get depending on which of these PDF sets you put into your analysis. Okay, very good. And yeah, okay, there is a small thing, but I think it's important because it's a general problem. So NMPDF 2.3, so this is a kind of self-criticism, but it was very important to learn it. So there were a lot of details related with the methodology, because then you have a big parameter space, you have to minimize things. So what we realized in going from one release to the next is that a change in the minimization thing, so in the little, in changing the fitting methodology, just the stopping criterion or the genetic algorithm, was shifting, for example, the gluon by a factor of 4%, okay? So it was not good. So at that point, we realized we have to be really careful on what methodology we use, because otherwise, the error band that we give are not reliable. They should be stable under the change of methodology, otherwise you are giving something which is not correct. So at that point, somehow we ask ourselves, how do we make sure, but this is not just for PDF fits, it's for any kind of fit you do. So how can you make sure that the fit you're doing is robust, so that it doesn't change as soon as you tweak a bit the parameters, you get a different result. And this is the idea of the closure test that I think now all the collaborations are trying to do. So the idea of the closure test is a statistical principle you assume that there is a known law of nature. So assume that the PDFs are known, so that this somehow nature revealed that the true PDF are the MSHT 2008. And you generate the data based on these PDFs. So you generate the data knowing the law of nature with them and the theoretical prediction. And then basically you fit the PDFs to this fake data, and then you check if your fit is able to reproduce the underlying truth, okay? So you can do 3 steps. So first of all, you generate 1,000 times the same data with the underlying law. At that point, you have to get a 0 chi-square, because the theoretical prediction and the data are not oscillated. They are based on the very same prediction. If your methodology is good, you get a 0 chi-square. And that was what was not good in our 2.3. It was not getting a 0 chi-square. We didn't have a good enough genetic algorithm to really explore the phase space and to go to 0, okay? Then you oscillate the data, okay, once. So you do the experimental noise and you check if you reproduce that. So this is telling you what is your flexibility in the parameterization. And then you do the full oscillation, the Monte Carlo plus the data noise. So this is nice. So this is what I was telling you. So with all the genetic algorithms, you were not going down to 0, even after many generations. And instead with the new genetic algorithm, you go to 0, okay? So level 0 is this. If the pseudo data are identical to the input theory, then the agreement with the theory should be arbitrarily good. So the chi-square should go to 0. But the PDF uncertainty goes to 0 only in the region where you have data. Remember, because even if you have perfect data and the chi-square goes to 0, if you don't have data, like in this region, the uncertainty should be huge because there is nothing to constrain the PDF in that region, okay? So this somehow is telling us something about the extrapolation uncertainty. Then level 1, you add uncertainty to the pseudo data, which is equal to the actual experimental uncertainty. And then you generate the replica fit the same data over and over again. At that point, the chi-square should go to 1, because that's when you have experimental noise. The chi-square is not 0, but has to go to 1. And there you test the equivalent minima. So the difference between that is because you have many different equivalent minima that give you the same good fit. And then you can generate Monte Carlo replica. At that point, the chi-square has to go to 2 because there are 2 fluctuations. And this is if you want the data uncertainty. So this way you can try to test, first of all, the reliability of the minimization algorithm and what are the different components of the uncertainty. And all the different PDF collaboration in one way or the other do that. So they try to see if I put something in, do I get it out? So do I reproduce faithfully the data uncertainty? Do I reproduce faithfully the law of nature if I was able to know it? So that's a very important test. And then the other thing that I think answers your question. So now there was a way there were several ways actually that people, so these are the first one by Thorne and Watchet and one by Stefano Carazza, to really go from one Hessian to the Monte Carlo. So if you like only Hessian sets, you can convert a Monte Carlo set into a Hessian using this MC2 Hessian algorithm. Or if you have an Hessian and you like the Monte Carlo, you can do the same. Okay, so there are now in these 2 papers that you can see here, they tell you the detail, but the interesting thing is that this big division is no longer there because you can go from one to the other. Okay, I think that's not important. Okay, I think, so this wraps up everything we had to say about the statistics and methodology. So let me just read. So the PDF determination with the Hessian method, you have a simple linear error propagation, you require the tolerance, and you have a possible parameterization bias. With the Monte Carlo, you have a 2-step procedure, the data Monte Carlo and the PDF Monte Carlo, and you can have a very general parameterization. However, you need an optimal fit to get a good methodology. And then the PDF representation is what I just told you. You can have a conversion between Hessian and Monte Carlo either way. And you can also compress the number of replicas. So if there are too many for your application, there are algorithms that allow you to compress the number of replicas to the optimal ones that you need for your problem at hand. And again, you can use either one or the other because the Monte Carlo is flexible, the Hessian is very efficient. So depending on what you need for that thing. So And then I also talked about the important thing of PDF validation. So we really need to assess the robustness of these error bands that we associate with PDFs. And that's it. I think that's all for today. I think I can stop here because tomorrow we look a bit about the theory aspects of what you put into the theory and what are the frontiers now for in the PDF determination. And I will mention 3 or 4, which I think I gathered from your interest so far. So I select a number of topics and we can talk about that. And then, of course, if you have other questions, we can discuss them. Thank you very much.
Okay, so from Zoom, it says it might be difficult to say something general about this, but how sensitive is the estimation of the uncertainty in the global fit to individual experimental uncertainties? As an experimentalist, I don't know how much I would trust what we provide, especially when it comes to systematics.
Very good question. So here is something that I didn't have time to talk about, but so this is the problem that, in a sense, of course, what we propagate is the experimental uncertainty. So experimental input is crucial, no? So if you were giving us uncertainty that are underestimated by a factor of 2, we have PDF uncertainty that in some measure are underestimated by a factor of 2. So I think it's important. But the crucial thing here, for example, look at this data. And this is not even the worst. So we have, and now we have even new data from the Z transverse momentum distribution. So you have the Z and the jet, and you look at the transverse momentum distribution. And now this is measured to a the statistical uncertainty is 0.5% for all the bins in PT. So, and everything is dominated by systematics. And the experimentalists tell us that they are all totally correlated. So, and what you can check is that the data theory agreement changes a lot by tiny oscillations. So for example, these are the data, okay? These are the theoretical prediction. So which one do you think is the best? So for example, the green one is much better than the blue. So you would say the blue is the best because it gets closer to the data. It's not true, because when the data are dominated by the systematics, what matters is only the shape. And any tiny thing in the shape gives a horrible chi-square. So the problem is that now, whenever we do this kind of fit, if the experimentalists give us super tiny statistical uncertainty and very, very precise systematical uncertainty, any tiny oscillation in your theoretical prediction or anything changes a lot the chi-square. So you have very, very large instability in the chi-square due to this super, not only clearly the experimentalists want to show that they have very precise things, but they somehow over-correlate things. And this thing of over-correlating, either you're super sure about what is the correlation, or it makes the life of the PDF fitters a nightmare. So I think your observation is super important. And we are getting to the point where PDF fitting collaborators internally have to cross-check the uncertainties that you give us. So, and sometimes we have to decorrelate uncertainties. Otherwise, we are not able to include the data into a fit. So that's a very technical problem, but we are getting really to the point where data are so precise that unless we do something with your uncertainties, we cannot put them in a fit.
A couple of comments. One is that there are also tools to do exactly what you're asking, which is to check the sensitivity of the PDFs to your data. And these are called L2 sensitivities. They have been developed by Tim Hobbs and the CT group. So it's possible to understand how much the certain data affect certain PDFs, and you can do a lot of games. So you may want to look into that. The other thing is that you are saying that you are not very sure as an experimentalist of what you are telling us. It's scary for me. I have blind faith in experimentalists. No, it's not true. It's not true in a very interesting sense, because with these fits, we can also check that your data are decent or not. And I have several stories that I can tell about times in which we found, not only me, I mean, it's a normal thing, but it's a nice way of collaborating and having feedback both ways. We need feedback both ways. And so one way we can give feedback to experimenters is to put the data inside the fit and check for deviations. So sometimes the solution is maybe we suspect that the correlation were overdone, you can decorrelate. Sometimes there are real systematic problems. So there was still some residual issue in the fit. I remember a fit of the zero data that we did on the W asymmetry. And there was a direct measurement of the W asymmetry. So they were reconstructing statistically the W that you cannot do because you have a neutrino and a muon, or a neutrino and an electron. So you miss the neutrino, you cannot reconstruct completely the W. So it's amazing work. And the zero brought the CDF idea to the next level. They did amazing work, really small uncertainties, which was very great for me because I was doing a D over U fit at large X, and that pushed the thing where I needed it. So we put in this data in the fit, and we find that it does not agree with all the rest of the data set of all the other experiments in the world. So what is happening? We mentioned this to the experimentalists, and we don't hear anything back for a couple of months, and then there is a revised paper on the web. So, and now they agree. So there are many things. It's a lot of feedback circles and ovals and shapes. So it's an important conversation to have between PDF fitters, theorists, and experimentalists.
Even because incompatibilities can be of different nature. So one is experimental incompatibility because they made a mistake in estimating things. But I think it's important to exclude it because otherwise incompatibilities come from the theory. So if you have an experiment that reveals some new physics, it doesn't have to be compatible with the bulk of experiments we have here. Because so I think it's important to single out the experimental incompatibilities so that then we can find the interesting one that comes from physics rather than wrong estimate of systematics or wrong reconstruction of the events.
And there is another side. There are real incompatibilities. You look at E866 data. We were discussing about the Drelian. You look at sequence data, and they don't look alike at all. So they're really incompatible with each other. And why? You ask Paul Reimer, a spokesperson of the E866, for example, and he was working also on sequences, and they're both right, good measurements. And they looked into it, and there is no clear answer why one goes down and one does not. So an interesting thing, which is again one of the frontiers, is how to represent the kind of systematic uncertainty. Is a systematic difference between the measurement of the same quantities. How to reflect this into these bands. This is not done in what you have seen today.
Exactly.
Except for this tolerance in which you say, whatever, I stretch my delta chi-square until everything is compatible with everything else. But
But you are blowing up uncertainty.
You are blowing up uncertainty. You might miss points. You might miss new physics because everything is inside the uncertainty. So you just fogging your lenses, and so it's important to also look into those kind of things.
Perfect timing.
No, first let's thank Maria again.